Hello students, this lecture is about to discuss the connectedness in topological spaces. So for this, first we have a definition of separated sets. Let X be a topological space and we take two non-empty subsets of X. These are A and B, and these subsets are separated sets in X if A intersection B closure and A closure intersection B both are empty. So for example, if we take two open interval 1, 2 and 2, 3, so these are separated sets because if we take 1, 2 intersection with 2, 3 closure, then it is 1, 2 intersection with, so its closure is closed interval, then it is empty. And also if we take 1, 2 closure intersection with 2, 3, then it is also closed interval 1, 2 and open interval 2, 3. So this intersection is also empty. So we can say that these two sets are separated sets. So now we discuss some other examples on the separated sets. So our first example is any two disjoint non-empty open sets are separated sets. So if we take two sets here which are disjoint, non-empty, and both are open also, so it means A is not empty, B is not empty, and their intersection is empty. So if their intersection is empty, which implies that A is not containing B, which further implies that A is containing B complement. If A is containing B complement, then if we take closure both sides, then A closure is containing B complement closure. Now A and B both are open sets, then B complement will be closed and B complement closure will be B complement only because it is a closed set. So closure of any closed set is equal to itself. So which implies that A closure is containing B complement, which further implies A closure is not containing B. So here we can write A closure intersection with B is empty. So similarly we can say that A intersection B closure is also empty. So these two conditions of the separated sets are satisfied. So we can say that A and B are separated. Then the next example, any two disjoint non-empty closed sets are also separated. So if we take any two closed sets which are disjoint and non-empty, so it means A is non-empty, B is non-empty, and A intersection B is empty, and A and B both are closed sets. So if A intersection B is empty, so we can say that A is not containing B, and further we can say that A is containing B complement. Now A is closed, then A closure is also containing B complement because if A is closed, then A is its closure. Now if A closure is containing B complement, then A closure will not be in B. So we can write A closure intersection with B is empty. So similarly we can show that A intersection with B closure is also empty. So we can say that A and B are separated sets. Now in third example, each pair of disjoint subsets of discrete topological space is separated. Now in the discrete topological space, we know that every subset of that space is open as well as closed. So if we take any pair of disjoint subsets, that will be open as well as closed also. So from the first and second example, we can say that each pair of disjoint subsets of discrete topological space is separated. So now further we define the disconnected space. A topological space X is disconnected if there exist two separated sets in X such that X can be written as union of these two separated sets. So if we take any topological space X and if we break this X into two parts, it is A and B, and these are separated sets, then we can write X as a union of A and B, and also these are disjoint, and it also satisfies this separated condition that A intersection B closure is empty and A closure intersection B is also empty. Then we can say that X is a disconnected space. And also we know that two disjoint non-empty open sets are separated sets. So we can define disconnected space in the terms of open sets also. So X is disconnected if there exist two disjoint non-empty open sets. Let us take A and B in X such that X is equal to union of these two sets and these are disjoint sets, then X is a disconnected space. Because two disjoint non-empty open sets are separated sets, so we can write X as a union of these two separated sets. So X is a disconnected space. And also two disjoint non-empty closed sets are separated, so we can define disconnected space in the terms of closed sets also, that if there exist two disjoint non-empty closed sets A and B in X such that X is equal to A union B, and these are disjoint also, then we can say that X is a disconnected space. So further we have some examples on the disconnected space. The first example we have, let X is a set here and tau is a topology on X, then X is a disconnected space. So X is disconnected because there exist two disjoint non-empty open sets. So these are 1 3 and 2 4 such that X can be written as union of these two, 1 3 union 2 4, and these are disjoint also, so X is a disconnected space. And now in the second example, a discrete topological space having more than one element is disconnected. Now we know that in the discrete topological space, every subset of that space is open as well as closed. So if we take any subset of X, X is a discrete topological space here, then A complement is also a subset of X, so which implies that A and A complement are open. So both are open sets and X can be written as A union A complement, and these are two disjoint sets also. So we can say that X is a disconnected space. So now we define connected space. A topological space X is connected if there does not exist two separated sets in X, such that X can be written as their union and these two sets are disjoint also. Or we can say that X is connected if it is not disconnected. So if we take one example, that X is a set which is containing 1, 2, 3 points, and tau is a topology on it which contains phi, X and singleton 2. Now we take closed sets by taking complement of each member of tau. So phi complement is X, X complement is phi, and 2 complement is 1, 3. So here we can see that there does not exist any pair of two disjoint open sets and closed sets for which X can be written as their union. So X is not disconnected, it means X is connected space. Now further we have some examples of the connected space. So first we have phi and singleton sets are connected in any topological space, because phi and singletons are the sets which cannot be written as a union of two non-empty separated sets. So these are connected sets in any topological space. Now in the second example, in the discrete topological space with more than one element, then singletons are only connected sets. So from the first example we can say that in the discrete topological space only singletons are connected sets. On the third example, an indiscrete topological space is connected. In the indiscrete topology, we know that only phi and X are the members of indiscrete topology. So there also does not exist any pair of two open sets or closed sets which can be written as their union and it is equal to X. So it is also not disconnected, so it is a connected space. Now fourth one is any interval in real numbers with usual topology is connected. So if we take any interval in the real line, so it also cannot be written as a union of two non-empty separated sets. It is also a connected space. Now in the fifth example, a cofinite topological space which is infinite space is connected. And we know that in the cofinite topological space which is infinite space, X cannot be written as a union of two disjoint open sets, because if there exist two disjoint non-empty open sets, let us take U and V, then we can write these sets are disjoint, so U intersection V is empty. Now if we take complement both sides, then it is U complement union V complement which is equal to X, because phi complement is X here. Now U and V are both open in the cofinite topological space, then U complement and V complement are finite. So which implies that U complement union V complement is finite set which is equal to X. So it is a contradiction because it is given that X is a infinite set. So there does not exist any pair of non-empty open sets which can be written as X is equal to U union V. So cofinite topological space is also connected space. So now further we discuss some results based on the connected space. So our first result is continuous image of connected space is connected. So for the proof, let X and Y be two topological spaces in which we take X is connected and we take a function f from x to y, which is a continuous function. Then we need to prove that its continuous image, that is f of x, is connected. So we will prove it by contradiction method. So if possible, let f of x is disconnected. So from the definition of disconnected, there exist two disjoint non-empty open sets. So let us take A and B in f of x such that f of x can be written as A union B, and these are disjoint. As A and B both are open sets in f of x, and f is continuous function, then if we take pre-image of these open sets, these are f inverse A and f inverse B are also open in set X. Then the union of these two open sets is given by f inverse of A union f inverse of B, which is equal to f inverse of A union B, and A union B is f of x, so it is f inverse of f of x, and it is equal to x. So x can be written as a union of two open sets which are open in x. So x is equal to f inverse of A union f inverse of B. And also if we take intersection of these two, so it is f inverse of A intersection f inverse of B, and it can be written as f inverse of A intersection B, and these are two disjoint sets, so it is f inverse of phi, which is equal to phi. So x can be written as a union of two open sets which are disjoint also, so which implies that x is disconnected space. But it is not true, because it is given that x is connected space. So we arrive at a contradiction. That x is connected space. So our supposition is wrong, that we have taken f of x is disconnected. So it is not correct, and which implies that f of x is connected. Now in this next result we have a topological space X is disconnected if and only if it contains a non-empty subset which is both open as well as closed. So for the proof, first we take X is disconnected space. Then we will prove that X contains a non-empty subset which is both open and closed. So if X is disconnected, so from the definition of disconnected space, there exist two non-empty disjoint open sets. Let us take A and B in X such that X can be written as a union of A and B, and these are disjoint also. So A and B both are open here, and if we take A equal to B complement, so it also satisfies this condition. Now B is open, so B complement is closed, so it is closed set because B is open, and we have already taken A is open set here, and A is equal to B complement, it is closed also. So A is both open and closed. And similarly we can say that if we take B is equal to A complement, then B is also both open and closed. So now we prove the converse part, that is, if a topological space X contains a non-empty subset which is both open and closed, then that topological space is disconnected space. So conversely, if we take any topological space X and we take any subset of X which is non-empty, and which is both open and closed, then we have to prove that X is disconnected. So now we have taken A is a subset of X which is both open and closed. So if A is open in X, then A complement is closed, and also A is closed. So if A is closed in X, then its complement is open in X. So now we have two open sets here, A complement and A. That is A and A complement in X, which are disjoint. So A intersection A complement is empty, such that X can be written as a union of these two open sets also. So we can say that X is disconnected. Now in this result we have that X be a disconnected space with the disconnection of A and B, that is X can be written as a union of two disjoint separated sets or we can say that these are two disjoint non-empty open sets, and also we can say closed sets, and Y is a connected subspace of X, then either Y is contained in A or Y is contained in B. So here we have, if X is a disconnected space and disconnections of X are A and B, so if we take any disconnection A and B here, and Y is a connected subspace of X, then we have to prove that Y is contained in A or Y is contained in B. So for the proof, let X be a disconnected space and there its disconnection is given, that is A and B. Two disjoint non-empty open sets. These are A and B in X, such that X is equal to union of these two, and these are disjoint. So Y is a connected subspace of X, where Y is a subspace of X, and A and B are open in X, then intersection of Y and A and Y and B are open in Y. So these are two open sets in Y. So now if we take union of these two open sets, so let us take union of Y intersection with A and Y intersection with B. So it is Y intersection with A union B, and A union B is X, so Y intersection with X, and Y is a subspace of X, so it is Y only. And also if we take intersection of these two open sets, then it is Y intersection with A intersection B, and these are two disjoint sets, so Y intersection with Phi, so it is Phi only. So Y is a union of two disjoint open sets here, and it is given that Y is connected subspace of X. So but Y is connected subspace of X, so it has no separation. So one of the open set must be empty here, so which implies either Y intersection with A is empty or Y intersection with B is empty. So from this we got Y is contained in A complement. So from this we get Y is contained in B complement. Now A complement is, so from here if we take A complement, then it is B. So if we take A complement in X, then it is B only. So Y is contained in B, and similarly B complement is A, so it is contained in A. So this way we have proved this result. If Y is a connected subspace of X, then either Y is contained in this A or in B. Now in this result we have, let A be a connected subspace of X, and if A is a subset of B and B is contained in A closure, then B is also connected. So we will prove this result by contradiction method. So if possible, let us suppose that V is disconnected. So from the definition of disconnected space, there exist two disjoint, non-empty, open sets, that is U and V in B, such that V can be written as U union V and these are disjoint. So it is given that A is a connected subspace of X and A is a subset of V. So it is connected subspace of V also. Now V is a disconnected space and A is a connected subspace of V. So from the previous result, that is, if X is a disconnected space with the disconnection A and B and Y is a connected subspace of X, then either Y is contained in A or Y is contained in B. So here disconnection of V are U and V, then so we have A is contained in U or it is contained in B. Now if A is contained in U, then A closure is also contained in U closure. Now let us take intersection of A closure and V. So A closure is contained in U closure, so it is U closure intersection V. And U and V are two separated sets, so this U closure intersection V is empty, so which implies that A closure intersection with V is empty. Now here we have V is equal to U union V. Which implies that V is contained in V, and it is given that V set is containing closure of A, so it is containing A closure, which implies that V is containing A closure. So from this we can say that A closure intersection with V is equal to V only. Now let us call this first equation and it is second equation. So from 1 and 2 we get V is equal to empty, but V and U and both are non-empty open sets in V, but here V is equal to empty. So but it is a contradiction. So V is non-empty, so our supposition is wrong that we have taken B is disconnected space. So from this we can say that B is disconnected space. Now in this lecture we have discussed about some results based on the general connected space. So in the next lecture we will discuss some results based on the connected space in real line. So thank you.